Okay, everybody, welcome to today's webinar, sponsored by AstraZeneca. Today I'm going to give you an overview of the lessons learned from the 2024 EQA scheme for molecular testing in lung cancer tissue samples. Next slide, please. Just a few housekeeping notes before we get going. So we've automatically muted your microphones to avoid any background noise. We are recording this webinar, so we will make it available on the EMQN YouTube channel shortly afterwards. It usually takes about, shortly being 2 weeks, but about 2 weeks to do so. Most importantly, it is an opportunity for you to interact and discuss and ask questions to me. So please use the Q&A facility on the bottom of your Zoom browser to ask questions. Keep them rolling in. We're triaging as they come through, but I'm very happy to answer as many questions as I possibly can within the hour we've got. Next slide, please. Your feedback, as always, is important, very important to us. It helps me and my colleagues to ensure that we provide high quality training to you. So after the webinar, you will receive an email with a link to a short feedback survey. It takes about 2 minutes of your time to complete. Please do complete it. It's very helpful for me for my own personal development as well to hear back from you about what you liked, what you didn't like, and how and whether what we're providing is constructive and useful to you. Next slide, please. Short disclosures. Next slide, please. I'm not going to obviously go into detail about myself, but I am obviously Simon Patton from EMQN. I've been involved in quality assurance for 26, 27 years now with EMQN. I've got a background in molecular genetics, but my passion has been throughout this time is improving the quality of patient care through my work, both within EMQN, but other organisations as well. And as an EQA provider, we've been established since 1997. We're based in Manchester in the UK. One point to note is we are what's called a community interest company, a company model that's based in the UK, specific to the UK, but really it focuses around social enterprise. So ensuring that all the money we generate, the profits we generate as a business goes back into providing good quality services for the likes of every user of EMQN. Next slide, please. Okay, next slide, please. Okay, let's get on to the meat of today's discussion, which is really sort of lessons learned from the 2024 EQA schemes for lung cancer tissue testing. Next slide, please. And before we really get into the details of it, for those of you who are not completely familiar with what EQA is, a quick overview. Promise it's only 2 slides we've got here. So really the principles behind an EQA is to ensure the quality of testing laboratories is assessed and audited in an independent and external manner. So we provide every laboratory with the same materials for testing. We coordinate the results, so all the laboratories send their results back to us. We coordinate that process. But I think that's the key point here is that the EQAs are designed to be a reflection of routine clinical testing. And by routine, I mean that when you receive the samples, we expect you to treat the samples as you would a patient sample. So that would be, for example, ensuring that any personnel who are involved in the routine clinical process has an opportunity to participate. So don't change what you're doing already for the EQA. And the results that you send back are benchmarked, if you like, against all the other laboratories performing that type of test, see how well the accuracy of your test compares to everybody else. But more importantly as well, the emphasis and interpretation you place on the clinical result itself. So the advantage of this process is it's an external measure of quality of service. But a big part of what we do is try to ensure that we provide continuous education and training for our laboratories. So we provide very detailed summary reports that aggregate the data from the entire EQA scheme, but we also provide you with a tailored assessment report, an individual laboratory report, which gives a measure of your performance in that EQA scheme. So whilst education is the primary driver behind this, we obviously do have to take note of regulatory frameworks, and regulation does ensure that laboratories participate in EQA, particularly if you're accredited to standards like ISO 15189. And they do also, and the regulators do themselves also take note of the EQA performance data. So it's certainly true that in many countries, if laboratories persistently failing their EQA, they can use that as evidence to suggest a weakness in their service provision and potentially close down the activities that lab related to that type of clinical test. Next slide, please. So this EQA scheme that we're going to be talking about today is the largest EQA scheme for lung cancer solid tumor testing. In the last 12 months, we had 342 laboratories from around the world participate. It's the 14th year that we provided this service to our laboratory users. And I have to thank the support, unrestricted access supported by AstraZeneca and Janssen to do so. As a laboratory, you have 8 to 10 weeks to turn around the samples, perform your analysis, find the results, and report them back to us. A key point here is that our assessment process, when we look at your results, is undertaken in a two-phase manner, if you like. So we ensure that every report, and you could imagine with 5 reports for 350 laboratories, that's a large number of reports are assessed. Every report is assessed independently by 2 expert assessors. So these are your peers who work in the field, have a deep understanding of lung cancer testing, solid tumor testing. We cover both the analytical component of the test process, but also we look at how you interpret that result and report it back to the referring clinician in the context of a clinical report. Our aim is to ensure that we provide you with artificial FFP samples that are accurate and identify different variants which are relevant to a typical clinical referral for lung cancer. We ask you to interpret those results in the context of that clinical referral in a way that's clear and concise for the end user. Our requirements are that you use a nomenclature system that clearly describes the variants you've identified or tested, that's internationally accepted and therefore standardized across the entire testing portfolio of every laboratory. And we also look for appropriate use of and accurate use of patient identifiers and sample information. Next slide, please. So a quick overview of the scheme. So this scheme is provided to you in the form of 2 sub-schemes. We have a lung cancer common biomarkers sub-scheme, which is designed to look at commonly tested biomarkers in EGFR, KRAS, and BRAF. And in fact, all 3 of those genes are mandatory for every laboratory taking part. This part of the lung cancer scheme is mandatory for all laboratories participating. Then there is an optional second arm, if you like, of the scheme on new and emerging biomarkers, where we have different challenges associated with those types of biomarkers. So it's mandatory in this case to be able to test for EGFR and KRAS, but optional to test for ERBB2 and MET. In both sub-schemes, we send 5 samples, and those samples are manufactured for us, custom manufactured for us by Revity, right, which you may be more familiar with the previous name, Horizon Discovery Limited. Using engineered lymphoblastoid cell lines, we typically ship scrolls rather than slide-based materials because the materials themselves are not suitable for staining and therefore triage through microscopy beforehand. And of the 5 samples, only one of the cases we provide is provided with a full clinical scenario where we'll be looking at the genotyping accuracy of the sample testing process and the interpretation and reporting. The other 4 cases, we only ask you to do the analytical test components, so the genotyping only, and we only score that part of the analysis. Excuse me. As in all cases for EQAs, we do an extensive amount of validation up front before we provide those samples to the laboratory. So this is in addition to the validation data that comes from the manufacturer themselves. So for all the samples provided in this scheme, they were independently validated in 2 different laboratories using 2 different relevant strategies on different sequencing platforms. Next slide, please. And the assessment process itself is it's well tried and tested now. We have a very strong set of harmonized marking criteria, which we've used for the assessment process over the years, and they're refined as we go through that. As we look, take the learnings from previous years, and we refine those marking criteria as appropriate for implementation in each given year's EQA. To do so, we have a team of 22 assessors from 12 different countries who are involved in delivering that assessment process. And you can see here the breakdown, should I say, of the countries of origin of our assessment team. It's worth noting here that we cannot do this without the significant support from the assessors. So a big thank you from me on behalf of the EMQN team to those people who have contributed to this process. Next slide, please. So just a breakdown of the data that sits behind the laboratories participating in the EQA. So here you can see all the data from 2011 for all the schemes that we've run over this time. And on the left-hand side, you can see it split out in the dark blue by new laboratories who've never participated in the EQA scheme before, versus the lighter blue, which is the existing laboratories, those that have participated at least once previously in the 14 years that we've run this scheme. And you can see that for 2024, there was a drop in numbers, about 25% or 20% less than the previous benchmark years, 2020 to 2023. And this drop in participation really reflects the fact we've changed our model for supporting this EQA to a partially financed model whereby laboratories pay a small proportion of the total cost of participation. And this is really done to sort of drive a recognition from a laboratory perspective that there is a cost to EQA, but also to try and minimise the risk of laboratories registering but not actually participating or submitting results, which can at times mean that other laboratories that do want to participate cannot do so because they've been unable to secure a place on the EQA. We have a set quota of laboratory spaces available, and it's important to ensure that we can have as many laboratories participating as possible. So that's really the big drop in participation numbers is accounted for by that change in practice associated with the cost of EQA. On the right-hand side, you see the data breaking down the participation numbers by region, and you see left 2024 versus 2023. And the key thing to note here is that although there's been a drop in participation, the real drive in increase in EU participation really is a reflection of the fact there's been a drop in Chinese participation, Chinese laboratory participation in 2024. So that the shift in balance, if you like, between EU and China has changed, and that really is the main reflection of the changes in participation data for those 2 years. And it's split out across both the common biomarkers here denoted by a CB and the new and emerging biomarkers denoted by an NEB. Next slide, please. So I've got a couple of slides for each sub-scheme to sort of run through the key points of learning from each sub-scheme. So we're going to start off with the common biomarkers version, which is the sub-scheme that all laboratories that participate in this lung cancer scheme must participate in. So next slide, please. So looking at strategies used by the laboratories participating, you can see that the number of laboratories undertaking analysis for all 3 genes is about 95%. Remember, those genes are mandatory to take part in this scheme, so it is always a surprise, if you like, to see laboratories that don't test all 3 genes. Our decision on mandatory gene participation is primarily driven by clinically relevant or clinically available therapeutic options. So when or by guidance from organizations like ESMO that say what you should be testing with respect to this type of diagnostic test procedure. So it's always interesting to see that a small proportion of laboratories that don't actually test for all 3 of the core mandatory genes. Looking at the technology used by the participating labs, you can see that targeted next generation sequencing accounts for nearly 61% of the laboratory's process techniques used in this process. With then an assortment of different strategies, primarily just real-time PCR or fluorescent PCR, which accounts for another nearly 40%, and then a smattering of other technologies, some of which are arguable whether they're an appropriate strategy to use. For example, Sanger sequencing, when you've got variants that could be well below the limit of detection for that technology, but less than 0.5% is a very small number of labs using that technology. And to be fair to laboratories, this is primarily used as an orthogonal approach in conjunction with a more appropriate technology like next generation sequencing. Next slide, please. So just a bit of detail about case one, and then we'll talk about the other four cases. So case one, if you remember right, from the original discussion, was a real proper clinical case. Obviously, this is all mock. These are not real patients, but we've made up the scenario to reflect real clinical practice, where we had a lady who is a long-time smoker, presented with a persistent cough and a shortness of breath during physical exertion. After admission to hospital, she's been found to have a mass on one of the lobes of her lungs, and also an enlarged bronchial lymph node. So she's had a biopsy. She's been diagnosed with that lung adenocarcinoma, and material's been sent from the biopsy for molecular diagnostic testing to evaluate the options for targeted therapy. And in this case, the sample we sent, we were expecting laboratories to identify an L858R variant in the EGFR gene, and no variants detected in the KRAS and BRAF genes. Next slide, please. So in a real scenario, the rationale for this case was this is pretty much a routine molecular referral for a sensitizing variant in the EGFR gene. We weren't expecting laboratories to find any other variants in the two other mandatory genes, KRAS and BRAF. And we were expecting the case to see how the participants interpret this effectively a routine clinical scenario in the context of lung cancer testing, tissue testing. It's worth noting as well that after the samples were sent, there was a change to approval process with relation to particular drugs in the US, which may have had an impact on the way laboratories could potentially have interpreted the results. Because this change came in after the samples were sent and shipped and the clinical scenarios were written, we didn't include this approval process in the assessment process this year. It will, of course, obviously be picked up at a later date in subsequent years, depending on the variants we provide. Next slide, please. So looking at the genotyping process, the analytical results, the full marks were achieved by 70% of the laboratories, so just over 200 laboratories out of the 300 testing this sample. We've got full marks for the analytical components of the EQA. We did have a challenging sample here in the sense that its performance in a variety of different testing scenarios was inconsistent. So we identified after validation and sending out to laboratories a problem potentially with sections for certain blocks, and therefore we just took a decision to only mark this case educationally, and therefore did not apply any associated poor performance criteria associated with it. So we were looking to see how laboratories handle a failed case a case with poor sample quality. 82% of laboratories reported that the test failed due to poor sample quality. The majority of those laboratories quite correctly requested a new sample or suggested an alternative methodology for actually doing the analysis downstream, for example, potentially using a liquid biopsy test. The remaining 18% or so of laboratories reported results, and 11 laboratories reported results with variants that we weren't expecting to find in the sample. And it's probably fair to say are not likely to be genuine in themselves. Next slide, please. So 5% of the laboratories that actually reported those results on a clinical report reported in that report that the testing had failed for a particular block. Most laboratories reported the expected L858R variant in EGFR. Bit of a tongue twister, that one, sometimes not easy to get right. So looking at more details of actually the reported results. So 82%, we already said, reported the test failed initially. 8.8% of laboratories reported no variant detected, and a further 8.8% of laboratories reported a variety of different variants detected, some of which were the correct variant, the L858R. I'm really struggling with this one today. Variant, and then a variety of other variants, as we talked about previously, that we were fairly confident weren't present within the sample. Next slide, please. So the real take-home message from this actually is if your testing fails, you should provide a clinical report as you would for the QA provider, as you would in the clinical setting. So having worked in a clinical lab for many, many years, the normal practice, certainly within the UK, is you to provide a report back to the clinician that said the sample would have failed testing, and you would, as a part of that process, ask for a repeat sample or offer an alternative option to actually continue the testing process. And really, we were looking here for a laboratory to make it very clear that the testing had failed, and to make it sure that the end user was aware of that. Next slide, please. Looking at the interpretation, of course, this is a sample that's failed. 70% of the laboratories received full marks as a consequence of that, which, looking at the data from previous years where we've had slightly different clinical scenarios, was an improvement on 2023. Obviously, this is a test where you haven't got in most cases, got a clinically actionable result. But still, we think that there's a significant improvement there. There is a real reflection on the quality of the testing process and the way the laboratories report that back to the clinician. And most importantly, there were no clinical interpretation errors as a consequence of the test process. Next slide, please. Moving on to cases 2 to 5, which, remember, these were genotyping only, so we weren't requiring laboratories to provide a clinical report. You can see that of the four cases, case 2, we were expecting laboratories not to find any clinically actionable variants in the 3 genes in EGFR, KRAS, and BRAF. And then the other 3 samples, each of them had a single variant within the genes of interest, EGFR, KRAS, and BRAF. And the variant allele frequencies, not particularly challenging, 5% for the EGFR, going up to 11% for BRAF. So these variants should have been detectable in a broad range of different testing strategies, possibly also including those which would be considered inappropriate for a lung cancer test. So the rationale for all cases, routine molecular referrals. Next slide, please. Looking at the genotyping results, so for case 2, there was two clinical errors, so less than 1%, one false positive, one false negative result. Case 3, is where we saw the most number of errors, so just over 2.6% of all the tests performed failed, so 8 critical genotyping errors. No false positives, one false negative, but the majority were either both a false positive and false negative, so missing the variant of interest and reporting something else, or vice versa. And 2 of them were related to laboratories misclassifying that variant as a VUS rather than clinical actionable variant. Case 4 had 6 critical errors, so just under 2%, spread across the range, and there was predominantly false negatives, false positives. And case 5, very similar to the first case, less than 1%, so 2 critical genotyping errors. These error figures are low, and it's good to see that is the case. And as we'll see in a short while, it's probably what we're seeing here is a reflection of real clinical practice in terms of the amount of errors laboratories make. Next slide, please. So summarising the performance data from this sub-scheme, there were 342 labs registered, of which 311 actually submitted results. The remaining laboratories withdrew for a number of different reasons, some of which let us know in advance, and others which didn't. Looking at the analytical performance themselves, there were 18 critical errors made across the entire sub-scheme, made by 13 laboratories. So just over 4% of laboratories made at least one critical error. And then breaking that down into how many errors were made by different laboratories, 10 laboratories made one critical error, 2 laboratories made 2, and 1 laboratory made 4 critical errors across the 5 cases, so a fairly significant number of errors there. There were no critical errors in the reporting process. And when you break down the participation data, so summarising by country here rather than by region, you can see that laboratories in China, Italy and Spain make up the large proportion of those laboratories participating in this EQA. Next slide, please. Okay, so pretty much a similar run through for the new and emerging biomarkers, but remember, this is a sub-scheme which participation is optional for all laboratories, and where we're providing biomarkers which are either more challenging or are up and coming within the context of lung cancer tissue testing. Next slide, please. So again, looking at strategies, remember EGFR and KRAS are the mandatory genes in the context of this test. So it's really good to see that 84% of laboratories actually tested both those mandatory genes and the 2 other genes of interest in the sub-scheme ERB2 and MET. 13% laboratories only tested the 2 mandatory genes, and the remaining 3% tested EGFR and ERB2. Again, breaking down the technique, you can see that here is a big check. There's a big difference here that the majority of laboratories have used a targeted NGS approach, with a smaller proportion of laboratories using a real-time or fluorescent PCR approach, and a very small subset of laboratories, 1.63%, who use a more genomic context NGS test, so whole genome test, whole exome test, should I say. Next slide, please. So looking at case 1, the sample which was sent with a real clinical referral, here we have a lady who has never smoked, but has a constant cough, and has been to see a doctor to try and understand what's going wrong. She's had a chest CT scan of her lungs, which has found a lesion on her right lung. She has 3 vertebral metastases, and she's had a biopsy, which has confirmed that she has had an adenocarcinoma. So she's then been, the biopsy has been requested to be tested using molecular analysis to evaluate the options for targeted therapy. And in this case, in case 1, we were expecting laboratories to detect a KRAS variant, a 35G2A variant, at 12% VAF. So again, not a particularly challenging variant allele frequency, but very reflective of routine clinical experience and practice. And we were not expecting laboratories to find any other variants in the EGFR, ERB2 or MET genes. Next slide, please. So the rationale for this case, again, just like case 1, a routine clinical referral. And although there's no clinically approved therapies for KRAS in this variant, we did highlight that the clinical trials are underway, specifically providing targeted therapy in this context. So this is us, if you like, utilising this scheme to assess the state of the art with respect to your understanding of the options for therapeutic treatments in future and present in the context of lung cancer tissue testing. Next slide, please. So 95 in laboratories, so just under 80% of laboratories achieved full marks for this case, so pretty high. There was 1 critical genotyping error where the laboratory incorrectly reported the presence of an ERB2 variant, which we have potentially identified as either a sample swap with one of the other cases, case 4, or some sort of mix-up in the test process. It could, for example, be booking in, it could be the actual clinical analytical process, or it could in fact also be the reporting process. It's really hard for us to tell where that lies, and it would be, the onus would be on the laboratory to investigate the actual causes of that problem. But certainly it looks like some sort of swap in the test process with case 4. It's important to one part of this scheme is designed really to sort of emphasize the importance of your test strategy and what's appropriate to use and what's not appropriate to use for a specific test. So in here, we really starting to try to dig into detail about how laboratories are testing for KRAS codon 12. Clearly, this is an important codon in KRAS that does have targeted and licensed therapy available for G12C, and therefore it's really important to make sure that you are using a strategy that can differentiate between the different codon, the different variants at codon 12. So if you are using a strategy that doesn't do that, then obviously it's important that you recommend that the sample is sent for further testing to try and elucidate exactly which variant in codon 12 is present within the sample. But more importantly, using a strategy that can differentiate between those different codon 12 variants is the core take-home message here. Next slide, please. Looking at interpretation, so just under 60% of laboratories got full marks. There were 4 critical interpretation errors, so that's obviously quite a lot higher than the corresponding case in the common biomarker subscheme. The breakdown of why those laboratories lost marks or got critical interpretation errors: 3 laboratories overstated the clinical utility of the G12A variant, stating that it may be predictive of response to a targeted drug for G12D inhibitors. As we talked about in the previous slide, there currently is no licensed therapy available for that. 1 laboratory reported a KRAS G12A variant in the results section, but then went on to talk about G12C variant being detected, which is predictive of response to treatment. Of course, they've mixed up the 2 variants here, and the interpretation is then followed on based on the wrong variant. Next slide, please. Looking at the 4 genotyping only cases, so cases 2 to 5. Again, case 2 was a sample with no clinically actual variants in the 4 genes of interest. And then the other 3 cases had a variant of interest in either MET, ERBB2, or EGFR. Again, the variant allele frequency is not hugely challenging, but challenging enough that we do detect problems associated with the test process. Also, quite honestly as well, reflective of what's available in terms of providing materials for these types of tests. So it is particularly with MET challenging and difficult to find samples that will reflect real clinical variants in the context of this gene. Next slide, please. Looking at a breakdown of the errors, again, the number of errors made were in line with, well, the percentage of errors made were in line with what we would expect to see in an established EQA. So certainly less than 5%. The most challenging samples were sample 3, the MET variant, and sample 5, which I think was EGFR, where the error rates were 4.1% and 3.28%. And again, when you break it down, you can see there's a mix of different reasons for why the laboratories are making errors. The majority were either false negatives or there are other types of errors. Next slide, please. So I focus really on variant 3 here, which is the MET variant. So primarily because this was the most challenging one for all laboratories doing the testing process. I don't think from a laboratory perspective it would be a surprise to you, but there was a lot of inconsistent variant nomenclature for this MET variant. Many laboratories incorrectly reported it, the intronic variant, as a frameshift variant, when in fact actually it's a splice site variant. Another key point we see is that laboratories, if you're only using a DNA test, you should also make sure that the protein change is reported as a potential protein, as a P brackets hashtag, to reflect the fact that the variant itself is the significance of the variant is uncertain. And if RNA was tested, then we would expect laboratories to confirm that the splice site variant causes exon 14 skipping, and the correct nomenclature for the protein change would be as shown on the screen here. So again, highlighting a challenging case is difficult to test for. There are different strategies being used by laboratories to do that testing, but if you do report it, you need to make sure that you infer to the end user the correct result associated with the type of test you've undertaken. Next slide, please. So in summary, for this sub-scheme, there were 134 of the laboratories who participated in the lung scheme participated in this sub-scheme. 123 of those returned results. There were 13 critical errors made by 8 laboratories, so 6.5% of all the laboratories that participated made a critical genotyping error. 5 of those laboratories made 1 error, and 2 laboratories made 2, and 1 made 4 critical genotyping errors. So again, reflective of the common biomarkers, the spread of breakdown of errors. There were 4 critical interpretation errors, so 3.3% of all the labs participating made an error that would potentially could cause patient harm for that patient based on the interpretation they applied to the correct analytical result. Breaking down the participation data in more detail, a big difference here is that the majority of laboratories come from Italy and Spain, whereas China, who had a high participation rate in the common biomarkers, has a participation rate reflective of the remainder of the laboratories participating in the scheme. Okay, next slide, please. So the key learning points that come out of this EQA scheme, so the performance data and the key learning points. So a few slides really to give you some overall overarching data associated with performance. Next slide, please. So looking at participation data and the performance that comes associated with it, you can see on the left-hand side the participation data since 2014. We only show a rolling window of the last 10 years. As a percentage of the laboratories, you can see that about 10% of laboratories this year didn't submit results or withdrew from the scheme, about 5% of each, an equal number. The remaining 90% of laboratories that participated in the sub-schemes did in fact return results for assessment. Looking at assessment scores, you can see, as we would expect to see a fluctuation in the mean scores for both the genotyping and interpretive components. This is a reflection of the fact that the challenges we provide every year are different, and we're asking different questions every year with potentially more challenging samples or difficult interpretation scenarios associated with it, and some years are easier than others. But what's good to see is that the critical error rates, which is reflected in the bottom right-hand graph, really reflects what we would typically see in a very long and well-established EQA scheme. So the average critical error rate across all of our EQA schemes, 90 plus EQA schemes, is somewhere in the region between 3 and 4%. And you can see here, although there's fluctuations given on different years, and that fluctuation splits between the genotyping or analytical component and an interpretation component, that score is less than 5%. And this really reflects what we would typically see as a baseline figure for the amount of errors being made by laboratories. And therefore, I think what is also reflective of clinical practice, that somewhere in the region of 97% of all tests undertaken for lung cancer will be returning the correct result, either in the context of the analytical process or the interpretation applied to that result. Next slide, please. This slide here is completely new to this presentation. So what I wanted to do is to present the evidence for performance monitoring, and more importantly, evidence to demonstrate the power of multiple participations in an EQA scheme. This data was reflective of this lung cancer scheme, and therefore reflective of 14 years worth of data. There's a large amount of data behind this, and so there's a strong confidence that the analysis we've done is reflective of real life. But what you see here is the data on the average scores by a number of participations and the poor performance data by a number of participations. So if we look at the left-hand graph, you can see the average scores for genotyping in the light green, in the light green, versus interpretation in the dark green, displayed for labs that have participated once on the left-hand side of the screen, left-hand side of the graph, versus up to 10 times on the right-hand side. And you see that the scores for laboratories that participated 10 times is statistically significantly higher than the laboratories that participated in the EQA scheme only once. And that trend is statistically relevant for both interpretation and the genotyping component of the test process. So in other words, the more times you participate, the higher the likelihood of your score, and that reflects a more improved performance over time. But more importantly, if you look on the right-hand side, these are laboratories that have performed poorly in the EQA scheme, so those that have been deemed to have made an error that potentially could cause patient harm in a real clinical scenario. So again, the data is stratified by those labs on the left-hand side of the chart that only participated once versus those labs that have participated at least 9 times on the right-hand side of the chart. And again, you can see that the more times you participate, statistically, the higher the likelihood of successful participation or the reduction in poor performance over time. And although the numbers are significantly less, there's still enough power in the analysis to indicate a trend that that the more times you participate, the higher the likelihood of good performance or passing the EQA scheme, and therefore the reduction potentially in patient harm as a consequence of it. Next slide, please. So a couple of slides really just going to in breaking down a few more of the key learning points associated with the test process. We'll focus on the analytical component, the genotyping component first of all. The standard genotyping was very high for both sub-schemes, so less than 2.5%, with more than 75% of laboratories scoring full marks in one or the other EQA scheme. So this is really good. It's reflective of really good quality testing within the context of lung cancer testing. And as I showed previously, that's reflected in the baseline error rate being somewhere between 3 and 5%. Laboratories, but there are a few other key learning points that we want to emphasize. So laboratories should always include the results of all the genes tested. So it's commonly seen that you only report the results of the gene that's where the variant has been found, whereas in fact you can see from the scope of the test from the laboratories they've tested many more genes, or the scope of the test is much broader than what's been reported. Important to emphasize: don't omit the genes that you haven't identified variants in. So or you can, for example, include a statement where no other clinically actionable variants were detected and should be included as standard if a variant has been detected in one of those specific genes. We also recommend that laboratories that have missed a clinically actionable variant due to the limitation of their methodology consider using other methodologies with a higher sensitivity and/or broader scope. And/or not limited analysis of particular hotspots. This is becoming increasingly important in the context of lung cancer testing, where we now have multiple different biomarkers, many of them which have got variants which could be spread out across the entire gene. And in 14 years after the implementation of molecular testing in lung cancer, the treatment options available for patients nowadays are so much broader that the strategy you use for your test process really needs to start to look at looking at a broad number of variants rather than using very targeted tests for specific genes or specific variants. We also recognize the importance of ensuring that laboratories use consistent nomenclature, and how you describe that nomenclature how you describe that variant with the context of that nomenclature is really important. We have, over the last 2 years, supported the implementation of the main initiative in the States, but we also totally understand that this is still in flux from a laboratory's perspective, and where possible, we would still we obviously recommend the use of a clinical relevant main transcript, but you can use other references, should I say, as appropriate, so long as they are consistent with the requirements of the nomenclature process. Next slide, please. Looking at the key learning points for interpretation. So just like the analytical component, we're also seeing a real improvement in the quality of the interpretation that laboratories are making on their analytical results. Many of the laboratories now do include interpretation. It is considered good practice by the assessment team, but we also understand that in some regional areas it's not possible to do that because of local testing restrictions. This is taken into account in the test process, but nevertheless, interpretation as a general principle has been done very well by all laboratories. The key areas for improvement identified in this year's EQA is Again, really reflecting what we've seen in the analytical process, just a small laboratories not providing sufficient details about how they did their test or what the limitations of that test is. And sometimes, for example, confusing things like analytical sensitivity with limited detection. The clinical interpretation that is, if you do provide it, should be tailored to the referral reason and the patient being tested. So again, whilst laboratories include interpretation, it's quite often generic, regardless of the genotype obtained. And obviously, this can be really quite confusing for the end user, and does mean that reports can be easily misread. So please do tailor your interpretation to the question being asked and the patient being tested. Next slide, please. Finally, some key learning points about the actual reporting and how laboratories are feeding these results back to their end users. So the standard of reporting has improved markedly over the 14 years. There's little really, to be honest, to say about that, other than to say that most laboratories now provide a report that's really good at referring the information back to ensuring that the end user can read the information, the key pertinent information. There are a few little take-home messages that are really details here about what you should and shouldn't be doing to improve that, before that, things like such as providing pagination, and particularly on multi-page reports. But one thing that has been a trend in previous years is that as the strategies utilised by laboratories have changed to more mutation scanning approaches using NGS, for example, we have in the past seen a lot of very, very long reports, some of which are 20 or 30 pages long, which, as you can imagine, from a user perspective, for a clinical user perspective, really hard to find the take-home message. This year, we've seen less evidence to suggest that that's a problem. So laboratories are producing reports that are more clear, concise, and of a length that they're still able to convey the important message to the end user, but doesn't require wading through pages and pages and pages of data about how the test was done and the variants of unknown significance associated with it. So a feather in the cap to the laboratories, keep going at it, making sure that you provide those reports that are easy to actually digest and inform the end user about what you're looking for. Next slide, please. Last couple of slides, really. So a few timelines for this year. So we're already running. We're running 2 lung cancer schemes this year. One for solid tumor testing and one for plasma testing. Those samples were shipped for the lung cancer tissue testing scheme in June. If you still want to participate in the lung cancer scheme, then do get in the plasma scheme, then do get in contact with us as soon as possible. There may or may not be, I can't tell you for sure, some places available in that scheme, but that scheme will be shipped in September. So do contact us via our office at emqn.org if you need to come, are interested in participating. Deadlines for those schemes reporting are coming up in the next couple of months, and we intend to try and finish the lung cancer tissue scheme by the end of December, and the plasma scheme, because of the later shipping in the year, reports in early 2025. 2026, that should actually say. Next slide, please. Finally, a few acknowledgements, because this is not my work. This is the work of the EMQN team, particularly Mel Cheetham and Arthur Maqsood, who've done all the hard work and delivered it on your behalf, but also the work of our scheme organisers, assessors, and our scientific advisory groups that help support this. So I've already said a big thank you at the start, but just to reiterate, thank you to all of those who've contributed to this process. It really does make this assessment objective and independent, and done by your peers who have actually participated and do deliver these services on a day-to-day basis. So a big thank you to our scheme assessors for helping and support us. Next slide, please. Okay, so that, in conclusion, is the summary of the key learning points from 2025. So I'm just going to now switch to the question and answers facility to see whether we can pick up any questions. So do give me a few seconds while we get that up and running. So, okay, so I have got a couple of questions that are coming in here. So let me just address them one by one. So first question is, do we see any correlations between technical failures and techniques used? So for example, next generation sequencing versus qPCR. So not unusual for this question to be asked. And the answer is no, we're not seeing any strong evidence of technical failures with particular technologies being used. Often the advantage of these types of EQAs with a large number of laboratories, everybody being sent the same sample, and in particular sent the same artificial reference sample, which has been manufactured to high specification with a known variant, versus, for example, a real tissue sample where obviously there's a little bit more uncertainty associated with the variant itself, primarily due to things like tissue heterogeneity. The advantage of our approach here is that everybody's getting the same sample. We can be very confident that when we do find a technical failure or associated with a technology, that's reflective of real real practice. So we haven't picked up in this lung cancer scheme, certainly in the last 5 years, any evidence to show that particular technologies is failing more often than another technology. That's not to say that we don't pick up the evidence of laboratories using inappropriate test approaches, for example, Sanger sequencing in the context of a broad mutation scanning type approach, where we would expect to see a more broad mutation scanning approach. So no correlation we can see with different technologies in terms of how they perform. Next question is, what's the most challenging type of variant for participating labs over years for detection and interpretation? That's challenging for me to answer, to be quite honest, because each of our EQAs every year is different. We put a lot of thought and effort into the variants to include, and each year we try to ensure that we don't include the same variants as we've done in previous years. So I think that's one of the strengths of the EQAs that EMQN provides, is that we're not asking you the same question every year. We are challenging laboratories with more challenging types of variants or easier variants, where we're trying to reflect what we would expect to see in routine clinical practice. And when we design these EQAs, the incorporation of variants is really trying to cover that. Of course, it's really difficult within the context of 5 samples to provide a variant in every different gene of interest. And in fact, it's just as relevant to provide a sample with no variants in it, which is why you see us nearly always incorporating what would typically be seen as a wild type variant. So the most challenging types of variants, I think really at the moment in the context of lung cancer testing, it would be EGFR exon 20 insertion deletion variants and variants in ERBB2 or MET. They're clearly quite difficult to pick up, and often those variants are related to copy number variants as well. So again, copy number testing, particularly in the context of somatic mutation testing, is really, really challenging. And although we haven't included many in this specific this scheme on lung cancer testing, we do offer EQAs for copy number variant testing, technical EQAs for copy number variant testing, and have covered it in the context of some of our EQAs for PARP inhibitor therapies in the context of breast and ovarian cancer. So, for example, this year we did include a copy number variant in our somatic version of the PARP scheme for breast and ovarian cancer, and there was a very large error rate associated with copy number testing in that scheme. So it is technically really challenging. And at the moment, the evidence is that there's a long way still to go for laboratories to make it a reliable test approach in tumor testing, and by definition, extremely challenging in the context of plasma testing. It's been done to a pretty good degree in germline testing, but of course you're now dealing with a sample that's compromised in many different ways and makes that process much more challenging. I think that addresses a question also about, did we assess copy number variants in ERBB2 and MET? Not this year, but it's certainly something we will include in other years. Are we collecting any information about turnaround times? So again, an interesting question in terms of are we reflecting real clinical practice? And of course, in real life, these referrals come through the door, and there's a level of urgency applied to how long you should be testing it. That's obviously it's really difficult to do when you're shipping samples around the world, and your urgency of testing is confined by how long it takes to get the sample into the laboratory itself, whether it's held up in customs, etc. No is the answer to is the honest and blunt answer to that question. We are not assessing turnaround time, and in most cases, we give laboratories what we would consider more than sufficient time to do this test. So 8 to 12 weeks is considerably longer than real clinical practice. And it is often difficult for laboratories to turn that test around within the 8 to 12 weeks for lots of different reasons. Or maybe it's people saving it up to the last minute and only reporting it at the last minute. So I don't think we'd get any meaningful data from assessing the turnaround time associated with the laboratory test in the EQA. Nice to do, impossible to do in real life, I think. Another question here about MET exon 14 skipping. So the variant we included this year was a variant that's associated with MET exon 14 skipping. Should we also include the protein nomenclature? So I think I did cover that in the slide. So yes, it is recommended that you do include the protein nomenclature in there. Obviously, we totally accept that's a prediction, and unless you've actually used an approach that would tell you specifically what's been the actual breakpoints associated with the exon skipping, but you should include protein nomenclature where possible in your report. Okie dokie. I think that was the last question for today. So I'm going to wrap up now. Just to say thank you very much indeed for giving your time to today's webinar, for dialing in. I hope the information that we provided you is a good summary of the EQA, how laboratories are performing in it, and more importantly, the lessons learned from the global approach to assessing the quality of biomarker testing in lung cancer tissue testing. So thank you very much indeed. I wish you all the best. Enjoy your afternoon, and don't forget to keep up to date with the EMQN website. We will be publishing the webinar on our YouTube channel in a couple of weeks' time. So if you want to get a copy of it and be notified, then please do either join the EMQN LinkedIn channel or drop us an email at office@emqn.org. Okay, thank you for your time and energy, and have a good afternoon. Bye for now.